Let me hit this. Well, everyone, welcome to Rust with Tom Wells. Take it away, Tom.
Awesome. Thank you, Andrew. So, yes, Rust. I know we had a chat last week, I think, and I might have mentioned Rust in one of those conversations with some of this team. And so thank you, Andrew, for saying like, hey, maybe we should have a follow-up session on Rust specifically. And I love talking about this kind of stuff. So big disclaimer before you think I'm a crazy person, but I am a huge programming language nerd. Like, I don't know, I love programming languages. I really have. Since I was a child, I've sort of listed at the bottom, right at the bottom, like all the languages. I went through my brain and going like, what languages have I actually written code that I would say is a little bit more than just a hello world? And it's like I've listed them there at the bottom, and I suppose it has some history to it. I think starting with GW Basic when I was 6 or 7 years old. And so the disclaimer here, and there's some examples of some of the books I took on my last holiday. I went to Copenhagen 2 weeks ago, and my wife was laughing at me and like, these are the 2 books I packed: Category Theory for Programmers and the Book of Monads. Now, these are like very famous books. Maybe you don't know them, but they're deep classic computer science books. So the disclaimer here is I'm a huge nerd. I get like very excited about these things. It doesn't necessarily mean that these things are good or bad, or that I'm trying to create an opinion in your brain. It's like, I suppose I've built opinions in this, and it's because I deeply get into programming languages. I kind of love looking at different features and understanding how those features evolve over time and how certain languages influence others over time, etc. If I get very enthusiastic about stuff, it's only because I love this stuff. Alrighty, so when we talk about Rust, I went through a code base and was like, hey, what would be a good example to show of some Rust? And I just kind of randomly picked this one out. And I was like, sure. Like when I look at this, I go like, because I understand Rust quite a bit, and I've like quite a deep and broad knowledge of lots of different languages, starting with some really nasty early ones. I look at this and I go, yeah, looks okay. But I can imagine that maybe younger folk who are maybe at the earlier parts of their careers, or maybe have not got such a deep and broad knowledge of languages specifically, might look at this and go, whoa, this is nasty stuff. Like there's a lot of shit going on here, right? And what I would say to you is it's kind of the same as this, is like, you know, when you walk into the record shop and you go, oh my God, there's a new Nickelback album. And we all hate Nickelback, right? You go, oh, it's nasty. This is definitely going to be nasty. But then you kind of know that the more you hear those songs on the radio and the more you listen to that album, you go, oh, it's starting to grow on me a little bit. And you start to appreciate some of the nuances of the instruments or the voices or the lyrics or whatever it is. You start to go, oh, this kind of starts to grow on you, right? And so the sort of analogy that I wanted to make is that starting a dev project is kind of like starting a band. So when you pick that first language, or you pick that language for that dev project, you're making a choice around the sets of instruments that you're going to be using while you put that composition together, kind of like forming a band, right? And this is very much my view. So like when starting a project or starting something new, I go, oh, I really want to choose something where I know I'm not going to be constrained to be able to like fully express myself as part of building out this project, or whatever it is. And of course, that's like very much based on what it is that you're doing. If you're doing something fairly standard or like fairly simple, fairly well understood, you kind of know that you can choose from a language that has a whole bunch of more limited features or more expected or simpler features, and that's okay. And you're not going to run out of headroom. But when you're looking at something more sophisticated, or something where you know there's maybe a whole lot of unknowns, or etc., where you're going to have to deal with quite low-level things, or you have unknown performance characteristics, in my mind, it makes sense to pick a language which has got a whole bunch of features that you know you'll be able to pick and choose from and craft composition of your software together in an unconstrained way. I'm always kind of looking, and I've been searching for this language for a long time. It doesn't exist. This perfect language that allows you to express yourself in any way or form, it does not exist. The same way that there's no single musical instrument out there that allows you to compose any kind of song, right? So that's kind of my analogy. I don't know if that makes sense to anyone. So I took that nasty looking piece of code, which really was like, I just chose a function in one of my code bases, one of our code bases, that was like, hey, this one looks like it uses a whole bunch of interesting stuff, and wanted to just point out some of the kind of normal features that you would see in most other languages, or in maybe a lot of other languages, maybe the expected features that you would expect from a good mainstream programming language. And here they are, like, and this is Rust. So first of all, and I'll go through each one of these. If any of these don't make sense, some of these are very computer sciencey in nature, and I am a computer scientist, so that's kind of what I try to map things back to. If any of these don't make sense, though, please interrupt me and ask me what that thing is, because I take these things for granted. So the first thing is, Rust is strictly typed. It's a strictly typed language. That means types are important. Every value or variable that is declared, or function that is declared, or structure or record or whatever it is, has to be strictly typed. Like, it has to have a known type at compile time. And so it is also compiled, and we can kind of see some suggestions that it kind of knows things about the size of those types. So that often, to me, points to it being a compiled language. It supports higher order types, which in C# I think you would call generics, but higher order types means you can have types that contain other types. That makes sense. So like a list of ints, that int part is so the list type is a higher order type. You can't construct it until you provide the lower order type to it, if that makes sense. So you can't just have a list of things. You have to say list of int, right? I suppose you could have a list of object, and object could be any type, but it's still a list of object. So it's specific on object. Rust is, of course, the same. So vec is kind of like a list, a vector of type message. And it kind of looks C#y, I suppose, in its syntax there, supporting higher order types. It is an imperative language, and it is a Turing-based computation model. So imperative means that it's kind of statement after statement. You can, as you're writing code, you kind of write it in an ordered fashion. Like, I want this to happen, then I want this to happen, I want this to happen. That's sort of, in my mind, I call that a Turing type language, where it's like operations run in a sequential order. And you can kind of see that in the language. It uses semicolons, kind of this happens, then this happens. Pretty clear that it's an imperative language. It would be cool to look at some non-imperative languages, maybe as a next episode, because they don't look like this at all. I talked earlier about it being strictly typed, but those types can be inferred. So the compiler can infer the types. That doesn't mean that those types are dynamic, though. They're still strictly typed. It's just that the compiler can know what the type is. So you don't have to specify the type. I think you can do this in C# as well, right? There's like an auto type, or you can leave out the type and have the compiler infer it. That doesn't mean it's dynamic, though. It doesn't mean the type can change at runtime. It is the type that it is at compile time. It's just the compiler can work out what type it is at that point. So Rust is the same, inferred typing. All values or variables are immutable by default. So there's a keyword called mut. So when you create a variable, I hate the word variable because it implies that it can be varied somehow. And that's like not the case. For immutable variable is like an oxymoron, right? So I call them values. When you declare a value, it is by default immutable. So it would just be, I don't actually have an example of a normal value being declared, but it would be like let compressed equals something, and that would mean compressed. The value named compressed is immutable. So everything in Rust is immutable by default. You have to specify the word mut in order to make it mutable, meaning that you can reassign it later on in your program. Then what makes sense next is, it supports namespaces. You can kind of see that there. This double colon thing allows you to refer to things either in other modules or inside other structures, or whatever. The colon, I think, is quite C++y in its syntax. So colon, wherever you see that, it means you're kind of referring to something in another namespace or inside another structure. It also supports enums, which is a bit of a load. I think I'll talk about enums. They're much more sophisticated enums in Rust than maybe C# or Java, in that they can be parameterized. Each of those enum constructors or enum variants can be parameterized, which is super cool. And I'll talk about why that is so awesome later. Supports operator overloading. So you can see that here there's like a comparison between things, and so obviously the not equals operator has been overloaded. I think this is just my editor making it look like this. It's a ligature. So that should just be bang equals or exclamation mark equals. My editor's changing it to that funny symbol. It also supports closures. So here's like an anonymous function or a predicate being passed into this function. So dot position takes as its argument a function. So this also tells you that the language supports higher order functions, meaning that functions can take functions as parameters. This should be unsurprising, I think, in any modern language. And in Rust, they're called closures, which is just really another word for it. You kind of see these ampersands everywhere as well in Rust. And they look, and it would be not a bad thought to think that they're like references or pointers in C and C++. And so they kind of are, but they're a little bit more sophisticated. I'll get in, and actually a lot simpler than references and pointers as well. I'll talk about that in the next slide as well. It also supports iterators. So you can see you can iterate through things in this kind of general iteration kind of mode. Another cool feature, which I put in the normal stuff bucket, but this might not be that normal, is pattern matching. It supports pattern matching, meaning that you can destructure objects like this. So you can't, it's kind of weird because it's on the let side. So ignore the little if, but you can go let something equals something, and you can unwrap the thing on the left. So I can take it out of its sum container, revealing just the thing inside. So revealing, so this is called destructuring in other languages, but effectively what's being extracted here is a value called pos being removed from a structure called sum in this line. So this if let is saying if pos is inside a sum structure, then run this code here. Otherwise, run this code here. So this is like and that's called pattern matching. We're pattern matching and then destructuring. We pattern match the sum, then we destructure the pos in this cool little line. And that's very powerful. I don't know actually if you can do this in C#. I don't think so. But I bet you there's a language enhancement out there wanting to be able to do this. One of the last cool things is there's no null in Rust, and that's a good thing. No languages actually need null. And so all modern languages you'll see will drop null. From maybe the last 15 years, null has been dropped from all new languages. It's just, there is no reason to ever have null if you have higher order types. So this little structure called option replaces null in all situations. There's no situation where you need null if you have the ability to build a higher order type called option. And so that's leveraged. And then Rust also supports implicit returns. So I mean, the kind of the last statement in your function, if you leave out the semicolon, is the implied return. You can, of course, do early returns like that, where you can see we are returning none earlier. But if the program ever gets down to this line, and it's the last one in the function, that will be what is returned. And that can sometimes be a bit of a gotcha in the language, but you get used to it quite quickly. Any questions on like any of these big scary words? Like, does some of that make sense? Anything like that like tickles your fancy that you would like described in more detail?
Tom, just a question around why everything is immutable. Is that purely from a performance perspective, or is it, what sits behind it? It's just out of interest. Yeah,
it's a good question. Yeah, very good question. So I would say yes, from a performance perspective. The cool thing about the mutability here is mutability is inside the type system. So the Rust compiler is carrying that mutability flag along with the types. So while it's doing type checking, it's going, yes, this compressed is mutable. And so therefore it's okay if someone reassigns it, right? However, most things are not. Most things are immutable, meaning that the compiler, yes, can obviously disallow you reassigning things, but it can also do a lot of optimization. If it knows for a fact that something is immutable, it means you can do a whole ton of optimization. Like maybe you don't need to copy those values around. You can always point back to the same original one. That's okay, because you have a guarantee that it's never going to change. So you never, ever have to make a copy of it, right? So that's a great thing. That's certainly from a performance perspective. I also think, though, from a developer user experience, it is much nicer to know what things are mutable and which things are not, because it kind of tells you how to use this thing. So if I'm defining a function, you can see that all of my parameters here, model, messages, available tokens, they are all immutable. So you are guaranteed as the caller of this function that your stuff won't ever be touched. You just know that. You only have to just see the function signature and you know that nothing will be changed. If you see the word mutt in front of it, it's like, this function might change my thing, the thing that I'm passing in. You know what I mean?
Yeah, and I imagine also for concurrency that would help a lot, to guarantee in concurrency,
Totally.
especially if there's a lot of transactional stuff happening at the same time.
Yeah.
Okay.
Yeah, absolutely. Yeah, absolutely. Yeah, quite right. Yeah, and there are some rules around. So, anything else?
Yeah. So I got one just on what you mentioned now, right, about the mutable stuff. So if that model, for instance, right, if it's mutable, like, wait, you said can you put a mutt at the end of that? So can you go colon mutt at the end of that? No, right?
Mutt string, yeah. No, you can, yeah.
Okay. So then you would make a mutable prop, right? And if you do, is it automatically then, if I call this function, right, compress to target token, model is str, that's obviously a value type, right? Do they have differences between value and reference types?
Yes.
I'm sure, right? Okay. So if that's a reference type, and I call that then from, I call compress to target tokens, and I pass my model object in my string in. If that gets modified in this token, if there is a mutable prop on there, it modifies it by reference, right? So then the caller's reference to that gets updated too, right?
Yeah.
Yeah. Okay, so I mean, that's kind of the C# with ref props, right? You can pass through with ref.
Yes, that is kind of what this is. There's almost a different model in Rust for what you are describing. So, and it's probably a little closer to the C approach for updating things, as opposed to having a difference between value types and reference types. Rust doesn't really have that. It has this notion of something called ownership, which I'll talk about in the next slide, which I think answers your question in a different way. But I think you can think about stuff like that. It does map to that idea of value types and reference types.
All right, cool. We're good.
Yeah. From a .NET perspective, do you have pattern matching in .NET? Actually, I'm not sure.
So I don't think you get destructuring in that format, though. I mean, JavaScript obviously has destruction, but I've never really tried to do it in C#. I never had the need in C#.
Do in C#, but it's mainly on case switch statements. It's got pattern matching built in, so you can destruct on a case that's met.
Yeah, Tom, they just added that. They added that fairly recently.
Yeah, that's new though, right?
Yeah.
Okay, cool.
Yeah.
Okay, cool. Yeah.
So that's
okay, it makes sense that they would put it in the case statement. Yeah. Yeah.
Okay.
Okay.
I don't know if I like the implicit return. Though, just a side note.
Yeah, sure. So the implicit, I mean, you obviously don't have to use it. You can write the word return there, no problem. But if you leave it out and you leave out the semicolon, that becomes an implicit return. The cool thing is the type checker is really good. So the type checker will like ensure that things are good. Yeah. It doesn't, because there's no concept of null. It's like,
sorry, that obviously only applies to the last line, right? So basically everything above the last scoped bracket, right? Because surely if I had a line like that in the middle of nowhere, it's not going to assume that that's the return, right?
No, yeah. Well, it's not the last line, but it's the last expression in that expression call. Yeah.
Okay.
Yeah.
Cool.
Yeah. We can look at that actually. There could be a cool example around playing with that, maybe. The nice thing about it is it does encourage, or it certainly doesn't limit a functional style of writing Rust. So someone who prefers a more functional style would be much happier with this idea of implicit return, as opposed to having to write the word return everywhere. So and it's kind of like, I suppose, arrow functions in JavaScript. There is an implicit return if there's only one expression, right? In arrow functions in JavaScript. So you can go like x equals.
The first line.
You're right. Am I right? Yeah, I think so. Only because I use it a lot.
It's actually the same as the closure that you have there on Rust. It's like, yeah, it's the same concept.
Right. Exactly. Similar. Exactly right. Yeah. Yeah. And so that's really pleasant to be able to write, like all functions are kind of have implicit return in them, whether they're tiny ones like this or big ones like this, which is kind of cool. So it's consistent at least. As opposed to JavaScript arrow functions, where if you open a scope, then you have to physically write return. Rust says actually just the last expression is the one. Actually, you'll get used to it. All right. Any other questions on any of this other stuff? We will dig more into the references, pointers, and enums, I think. Okay, happy. All right, so here's the less normal stuff. That previous thing was like, all of that shouldn't feel too weird. Here's the weird stuff in Rust. Some of it's more weird than others. So traits are kind of like a more powerful version of interfaces in C#, but if you've written Scala, I think, actually, I don't know about Kotlin. I think Scala supports traits as well. So traits are like maybe a nice evolved version of interfaces in other languages, Java and C#, right? Which is where this thing exposes these kinds of functions, but you don't provide the implementation, right? The object itself implements a particular interface. That in Rust is called a trait. There are no classes in Rust, but you can write in an OO style, and that is really just through the C approach, which is like you declare a struct, and then you can attach functions to that struct. That's kind of OO, and then you can implement traits if you want interfaces as well. But traits can also be used in other ways, which is super nice. So traits are a very flexible kind of interface idea, but that is not just bound to OO, but can be used with objects in order to do something like OO as well. So they're a little more powerful maybe. And in the functional world, if you have ever used something called type classes, you can use traits to implement type classes as well. So they're super nice that they're not just bound to object-oriented approach. They can also be used in a functional type class kind of way. Rust also supports macros as well. And this might make you want to vomit. If you came from C and C++, like macros were awful and were often like a requirement that even including like if you had a dependency, I wanted to like include some other file in my program because I wanted to refer to it. Hash include was a macro that actually literally copied the contents of that file into your file. Macros in Rust are a lot more powerful, and I won't dig into the detail, but the macros in Rust actually allow you to process the syntax tree of Rust. So you have the ability to generate Rust code using macros really easily. Not that easily, but you have good hooks to be able to do that, which is super nice. So it means at compile time, your macros can generate you can write macros that would generate a whole ton of Rust code for you while the compiler is running. And that obviously makes the language very powerful and very extensible for all sorts of different things. Like, for example, in the future, you might want to generate a whole lot of code because you have some like database table or something. You want to pull those entities out of the database as entities inside your code. Like 100% you would write a macro to do that. Or probably you'd use some open source project's macro that does that for you. So macros are really nice because they allow you to generate code inside the compilation step. So as you run a compiler, the macros will run and expand. You can also do analysis inside those macros. So any code that is being processed, you can analyze inside a macro. So you can even use it to augment code. So you can wrap macros around structures. You can even wrap them around functions. You can even wrap them around code blocks. So you could say, hey, this code block is, I don't know, is a, like everything in it must be, any string used inside this code block must be uppercased or something. So you could write a macro that is an uppercasing macro, and it processes the code inside its scope. And wherever it finds a string, or I suppose it would have to be like a static string, wherever it sees a static string, it would uppercase the value of that static string during compilation, so that the compiled version only has uppercase strings in it, whereas your source code had lowercase strings or whatever. So you can do really cool stuff with macros. They're really powerful and quite complex, I suppose. You've got to understand the syntax tree, understand a little bit about compilers, but they're usable. And you'll see them kind of everywhere in Rust. The other very interesting thing here, and this has got to do with ownership. So let's look at this piece of code down here, toss blob around. And this maybe speaks to your reference or value types story, is that the compiler has, so in the history of languages, there's been two ways of dealing with memory in the past. The one is manually. So that is C and C++'s approach to memory management. Wherever you create a new object, you kind of allocate it onto the heap. And whenever you no longer need that object, you must deallocate it or free it from the heap, right? So that's the C and C++ approach. It's like manual memory management, and a few other languages as well. More recent, maybe more mainstream languages have said that that's too difficult, and it absolutely is. It's a nightmare for developers to track and manage memory themselves, because it's not that clear often if you're passing objects around, like at what point do I free it? Sometimes it's totally non-deterministic as to when should this piece of memory be freed, especially if it's being passed around and copied all over the place. At what point should I free it? And in C and C++ world, that was your problem. You had to figure that out. You had to go and say, no, at this point, I must free it. Or you could choose not to, and then you would have a memory leak, right? And maybe that was okay too. A lot of the time in C and C++, you were making this trade-off. Do I really care, or should I leak memory, right? Java, C#, all kind of modern languages, I suppose, solve this problem through the garbage collector and saying, hey, you can allocate as much memory as you like, and we will internally do the accounting around figuring out when a piece of memory is freeable. And that would have a runtime impact, right? So you as a programmer could just write whatever code you like. You could copy, pass things around, pass even like children inside other objects around, and then stop, like throw them out of your scope, stop referring to them. And you'd have this other process on the side that would every now and then run and go, let me just quickly check if this object is still being used, and would have to figure out, it's kind of like the graph of references to it. And if there's no longer anyone pointing to it, it could then free it, right? That's what the garbage collector is all about. C# Java made this thing very famous, and that's great. It's a pretty good model. There is, of course, a performance impact to the garbage collector. It runs every now and then, and while it's running, your stuff is not running, right? And it's running on the same CPU as that your stuff is trying to run on. So of course, there's a little piece of impact there. And it does a sophisticated piece of work as well. So it really has to understand an ownership graph. It's not just as simple as knowing who points to it, to a piece of memory, because it could be what something inside of that object might still be pointed to, right? So maybe nothing points to the object, but something inside it is still being pointed to by something else. So that makes it like a tree problem. You've got to look at a tree of memory being pointed to. So not only does it steal your resources, but it's also got a pretty hard job of figuring out ownership. So the garbage collector certainly has an impact. Rust has invented a third type of memory model, which is more similar to the first, where memory is manually managed, except instead of the developer figuring out when a piece of memory must be freed at compile time, the Rust compiler will figure out when to free it at compile time. So this is not, so the Rust memory model is a zero impact runtime memory model. So the compiler is figuring out when a piece of memory is not being used anymore, and will effectively implicitly put in a free statement where it believes that to be the case, if that makes sense. So that means you end up with the performance of C and C++, kind of where memory is deterministically freed, and there's no analysis of the garbage collector or ownership graph required. There's no runtime impact either, but without the developer having to do that itself. And so obviously it can't just do this for free. What it needs, it sometimes needs your assistance in order to understand how ownership of objects work. So the Rust model is this thing called ownership. Every object, like this thing blob, this is like a equals new blob kind of line, kind of currently set to the value A, and then we create a B. So we've got two blobs in memory, one pointed to by A, one pointed to by B. The way you would say this in Rust is you would say actually owned by A. A owns this blob, B owns this blob. If A and B had to go out of scope right now, after these two lines, the compiler would know for certain that it could free either that blob or that blob. So because it knows that A owns it, on this line, 64, we actually change ownership. And we say, hey, C now owns the blob that was previously pointed to by A. At this point in time, A no longer owns the blob. In fact, it cannot be used. So for the rest of this function, and you can kind of see there's a little compiler, little error popping up here, is that A cannot be used. It no longer points to anything. It doesn't have an object. It's not a thing anymore. You cannot use it. Can't refer to A at any point because A has died at this, because whatever it pointed to was passed over to C. C is now the new owner, meaning that I can now print B, print C, no problem. And the compiler knows for certain that when B and C go out of scope here, that it can free blob A and blob B. So there's a little bit of maths that goes on by the compiler to figure out when to free objects. That gets figured out at compile time. And that's through tracked ownership. And this can look pretty weird, right? For a .NET person, you would go, no, A points to the same object that C points to. In Rust, that's not the case here because I've gone equals A and C has become the new owner. What I haven't shown here is actually that you can have someone point to the same reference as something you point to, and it creates something called borrowing. So you have ownership, which is like ownership. If you go out of scope, whatever you own gets removed, but you can have other objects that refer to it, and that's called borrowing. So you can have another object that comes and borrows your object for a little while, and then when he goes out of scope, the ownership transfers back to you as the original owner. So you've got ownership, and then you've got borrowing underneath. I'm not actually showing you a good example of borrowing other than up here where it's a little complicated. But here we have a function called duplicate one of these. Ignore this lifetimes thing. But effectively what this function does is it borrows a blob and it borrows a blob. That's what the referencey ampersand looks like there. It doesn't take ownership of either of these two blobs. It's just like it's going to borrow it for a while. And when foo goes out of scope and bar goes out of scope, the original owners will get back their ownership of the blobs. I don't actually show that as a good example. I could actually, we could play with this if you were interested in it. So that's ownership. And this is probably the hardest thing in Rust. The biggest barrier is like figuring out how the hell this ownership works, because there's nothing that no one has ever seen this before. I can guarantee you haven't used the language that has this model. This is a completely novel model, and it's a good one. It is really a good one. It's very interesting. It does work well. However, there are some other caveats, like sometimes you don't know, like this function, duplicate one of these, borrows a blob and borrows another blob, and then it returns a reference to a blob, right? Ignore this little, what would you call it? Quote R thingy, which is called a lifetime. If it was just blob, blob, and blob, and it was a reference to it, the compiler goes, well, I don't know which one you are returning. Is it the foo one or the bar one? Maybe it's one of those. So I don't actually know. And that's what lifetimes are all about. Lifetimes is you're helping the compiler saying, this blob that I return has the same life as foo and of bar. So from an ownership and tracking perspective, you can consider them to be the same. And that is true because I am returning foo here, right? So I'm returning back the thing that you passed me, but I could have equally returned you bar. The compiler goes, wait, these two things are different. So here with these lifetimes, I'm saying, no, they're the same. It doesn't matter which one you pass me. These things have the same ownership, same lifetime. So I just wanted to show this to you. I don't think I can teach you how this works. You need to kind of work through a whole bunch of different examples, but this is the less normal stuff to Rust and probably the biggest barrier. The other very last thing, which I thought was also less normal, is it is probably one of the best compilers. The compiler errors are probably some of the best I've ever seen in a lot of languages. And it is really helpful around, maybe because it has a whole lot more context around the ownership of objects, but the compiler is a super good compiler. It really can teach you Rust just by going through compiler errors. Like it makes suggestions. Borrow of moved value A. Okay, maybe some of this sounds a bit Greek. Borrow of moved value A. Move occurs because A has some type which does not implement copy. Okay, so that's like a weird one, but that is suggesting that, hey, maybe you want to make a copy of this thing. And I tried to, but you don't implement the copy trait. So it's like, okay, maybe what you meant here is don't change ownership, but create a new copy of it. And it shows you kind of line by line, line 64, 62, 60. So it's like the error occurs here at 66 somewhere, but it shows you where there are like referring lines to this thing. You can kind of see even my IDE is highlighting it. Like, got something to do with this A, something here, and something there, right? These 3 lines at fault. And the compiler is explaining to you what you've done, which is really nice. I don't know. It helped me a ton learning Rust. It's just going through compiler errors. Any questions on this stuff?
Yes. I don't know.
Yes.
They're good ones.
I will go.
Hi, Tom. Yeah, 2 questions. How would you, for the sake of example, implement the copy trait to blob?
Yeah, it would be easy.
I missed
you
the
could...
first bit, so I'm not sure if you covered this already.
No, I haven't. No, and I wasn't planning to, but you can probably just derive it if you wanted to.
Okay.
But copy is just a trait, and so it's just something you could implement. Yeah, I could show you how to do that very quickly. So it would literally look like you would go, oopsie, and it's these traits are a little different to interfaces. So in interfaces, you would see, so you would go, actually, let me just create, doesn't matter. I was going to be pseudocodey.
No,
so say we
fine.
had blob like that. In .NET, you would kind of go like implements or something, copy or something, right? And then you would implement it in here, the copy function, right? In the way traits work, traits are a little bit more powerful, as I said before. So, and their implementation is done kind of elsewhere. So you would go implement copy for blob, something like that, and then you would implement the copy function being passed like a self. You know what I mean? So you still have a structure.
Yeah.
And even, in fact, adding functions to, if you were writing an OO style thing and you wanted functions attached to this blob, you would go implement blob, and you would have like, my funky function attached there. And this is called, the cool thing about this is these are type classes, meaning that they're not attached actually to the function, and they're scoped as well. So this copy only comes into scope if this file is in scope, right? Meaning that I could also implement copy for string, other people's stuff, right? I could implement copy for Will's struct, etc. Which is super nice. I don't have to go and change your code. I don't have to take your struct, which is in your code base, and go and hack my implementation into it. I can do that sort of on the outside.
Okay, brilliant. Very interesting.
Which is pretty neat. Pretty neat.
Yeah.
Yeah. Maybe feels a little foreign though, because you go, oh, that feels weird. And it's like, no, yeah, it's pretty cool actually. Often this model is called type classes in other languages, type classes or traits. So I think Scala called them traits. Other languages called this idea type classes, as opposed to interfaces, which are 100% OO only, right? Interfaces are an OO thing only, whereas type classes and traits can be used like interfaces, like we show here. It kind of looks like an interface, but you can also do it for other structures. Like it could even be, hey, if I want to implement copy for list of strings, I can add this copy trait to any type, which is pretty nifty, right? So anytime I have a list of strings, I suddenly have the copy functions available to me. Maybe extension methods in C# are similar to this. Yeah. So in one thing called traits, you can do extension methods and interfaces. They're useful for both. C# has got 2 different things, which I don't know. Yeah, just different.
Looking at that, it looks more like an extension method than it does more of an interface, right? I mean, an interface is really just defining what the contract looks like, right? I mean, there you're actually defining the implementation, right? The concrete implementation of copy, the function, right?
But I haven't defined the trait. Yeah, so I would have like, say it was my own copy, I would say trait copy. This is the interface. It's like copy must do something. And I don't define any implementation here. But I've created a trait, this idea of copy.
Keyword is actually the interface, really, right? Okay, with you.
Yes.
Got it.
Yes. But the cool thing is you can use it like an interface, like there, or you can use it like an extension method, like here. They're the same thing, actually. So traits are, that's why I said to you, they're more flexible. So you only have to learn one thing called trait, and it's a powerful thing that you can use in many different ways. Yeah. Yeah.
Very cool.
Happy with that? Yeah. Okay.
Yes.
Okay. So if you were interested in learning more about Rust, I actually do go into more detail. Here's my shameless plug, but I do have a YouTube channel and I have made a Rust like series or playlist. There's 5 videos, they're very short, they're 20 minutes each or something. And it goes through a bit more detail around each of these things. So you're welcome to go and do that. I didn't want to repeat that whole thing. I could if you want, like go watch the YouTube. But then I thought I'd get through this quicker, is I could show you something. These were my ideas. Shall we quickly do something interesting? I know someone earlier last week talked about Golang errors, and I thought I could talk about how those are maybe nicer in Rust handling errors, or how so Rust doesn't have exceptions either. And so how does it handle things like exceptions or errors? Golang does it one way, Java C# does it another way, Rust does it another way, but it's not a surprising way. It's a fairly straightforward way using enums. So I suppose I could talk about that. Or another stretch idea could be build a small web server. What do you guys vote for? We have like 7 minutes, I know, so maybe not enough time.
I think we build a web server in 7 minutes.
Yeah.
You want to build a web server?
I want to push your skills there, Tom. Let's see how quickly we can do this. Show me the power.
Yes. So building a web server is very easy. Okay, let's do that. Do you have an editor somewhere? Yeah, this one. Okay. Well, building a web server will be fun because we'll have to, oh yes, I did write that as well. Anyway, so here's how we start a new project. Is this big enough? It's like an empty directory, right? So there's a package manager called Cargo. Let's go Cargo in it. Cargo and Rust come together. Cargo is the build tool. It's like NPM and Node, right? Cargo is NPM. Rust C is the compiler. You never use the compiler, you just use Cargo. So Cargo init will create me a very small project. I'll make this bigger. There we go. And in it really is very little. Like this is an important file, cargo.toml. I don't know if you guys are familiar with I invented it, TOML, the TOML markup language. And I didn't invent it, I'm just joking. But it's kind of like your manifest, like your package.json, right? Similar kind of thing. And in it, you specify any dependencies. By default, you just, it's just put in the basic stuff. There's different versions of Rust as well. So you can target older ones. 2021, I think, is the current stable version. I think you could even use a more unstable version of Rust if you like, but generally you don't need to. And then it's just written us a quick hello world. So we can just go cargo build, and that'll compile it. And we can go cargo run, and that will run it. And we can also go cargo watch -x run. And this will then put us into like a watching kind of mode. If anything changes, it'll recompile and rerun. That's what that -x run means, is like watch the project. And when something changes, I want you to recompile and then do what? Oh, it's run. Because I could have said, I want you to rerun my tests or something. So that could be -x test. But we're just going to go run. So we could say, hello, everyone instead, press save. Like the watch detects it and reruns it, right? So that's super cool. Super nice, simple sort of flow to start with. Okay, so if we're going to build a quick little web server, what I would do is we go look at crates.io. This is like the global package management, like NPM. This is the global repo. And if you knew Rust, you would know that rocket.rs is one web framework. It's a pretty good one, pretty popular one. It's not the only one, but it's one I'm familiar with, Rocket.
I love those developers.
Oh, this is a web.
Like 0.4.
Say again?
We haven't even hit V1 yet. I love those beta tested versions.
Yeah, exactly right. And it'll get even worse. So if we look at the versions of Rocket, it's like, is actually, and that's kind of the one they suggest you use. So this is one of the issues with Rust, is it's a very new community, right? So it doesn't have the years of maturity. It's only kind of 10 years old or something. So you do have to deal with a little bit of unsophistication there. But typically, I would say you can expect to have a very stable experience. Rust never crashes. The compiler does not allow you to write code that crashes.
So my next question was sort of going to be like, what's the actual support like on those packages, right? Like, I mean, like, how often do you end up with like bugs in them, or like you find weird things that don't work? So I mean, you even get that with NPM, right? I mean, that's a mature sort of framework for packages, and even then, like, you get a lot of problems with npm packages, right? So how's that experience been with Rust?
Well, it's the same, right? So I mean, it's not, you still have to go and do your due diligence around that project, and see whether it's a project that you're willing to look at. But
well, I mean, like, I'm taking Rocket,
like
right? Rocket being your package, or I mean your server side thing, right? If I take, like, I don't know, let's even take something like like Axios, right? Axios has a bunch of issues, right? Like, there's constant problems within that library. So I mean, like, with the compiler being as good as it is, you'd hope that they'd be able to minimize the bugs they introduced to the system. I guess. I mean, I don't know. I'm just winging it here. So I'm asking, what's that like?
Very few runtime, very few. I would say very stable, a very stable experience. But sometimes you do find yourself having to dig through people's code to understand what is going on. I mean, you're not free of logic issues, but you are pretty much free of runtime errors or things being null or whatever. I would say it's generally pretty stable. But what can often be missing with newer ecosystems is, like, just like there's some feature that you use in OAuth or something, like SSR, server-side rendering in HTTP. And it's just like, the web frame you pick, the developers never got around to building SSR yet, right? So you could just not have that, or maybe they don't support WebSockets or something. So you've got to just make sure that you do your due diligence. But like, and here's the experience. So like, let's add. I just literally clicked there. Let's add Rocket to our package. There we go. So the cool thing about packages is they also support this thing called features. So when you publish a package as a package maintainer, you can, when someone imports it, you can have a bunch of switches that they can turn on and off inside your package, which actually changes the compilation of your package. So here you can see that by adding Rocket, the only feature it's turned on by default is HTTP2, which obviously is to support HTTP2, but they haven't, just to keep the package really small, is I've not got JSON or message pack or MTLS or any of these other things compiled into this package. So Cargo is going to compile this package as well. So if I go cargo build now, I'm recompiling this package. I'm recompiling Rocket based on those switches. And if I go and look at my TOML file, I can see that it's added Rocket. Look, it said this is currently not the latest version or the latest stable. It's saying actually, so my extension is a really good one called Rust Analyzer. It's the only one you ever need. It's excellent. Rust Analyzer is amazing. If you hover over these things, you can see all the versions of the package, and it'll show you things like this, like, hey, you're using something that's not the stable version, which we did see. And 0.4.11 is the current stable one release, whereas this is pre-release. So it's showing me that, which is nifty. Compile happens there. And then it's like, well, let's look at their example. I'll just paste this in because I've got 0 minutes left. But like, okay, so there's kind of the import statement. Let's look right down at the bottom. This is like the main method function Rocket. And this is kind of launching the web server, I suppose. And it's, so Rocket is pretty cool. It's very similar to Express, right? Where you can mount different routes and different handlers together. So here we are mounting the /hello to this list of routes. And that list of routes contains only one function called hello, which is this one. So we're only mounting this route into /hello. So I can kind of see that the URL should be /hello /name/age, right? So let's just try it.
So
run, and then Rocket launches.
Those hashes, those are what? Derives, right? Or what are they called? Traits, right? Launch is a trait in this case.
This is a macro. So this is running the launch macro.
A macro. Okay, so
there's code generation.
Okay. Then that belongs
this
to
kind of tells
Rocket,
you this. Right? Yes. So this is Rocket's launch. Yeah. If I hover over it, I can see it. Yeah. And see that it's like, it gives me the docs. So you kind of know wherever you see macros that code generation is happening underneath. So this is probably generating my something, like the main method, I imagine, or whatever.
Yeah, that probably generates like a main function, which is automatically exported via your main.rs. Right? Because I mean, otherwise, how's this thing going to know to start, right? Surely main is always the entry.
Yeah, right? Exactly.
So it wraps it up.
It tells you. So
okay, it literally says that. Okay.
So generates a main function that launches it. So you don't have to do this. This is obviously the simplest way to do it. You could, of course, call launch yourself or write your own launch, but this is obviously the built-in sort of simplest way.
Yeah.
And then you'll see that get is a similar thing. Like get is also generating some code. Yeah, I'll show you something really cool though. So here I probably don't even need to prove to you that it works, but if I go /hello/tom/4042, it works, right? Here's something super cool, and maybe this is the last thing, but maybe I changed, like I want to add a new attribute here, like age and shoe type or something. As soon as I press save here, you'll notice I get a compiler error. It's like, hey, wait a minute, you've got a shoe type thing here, but like your function doesn't handle the shoe type thing. It's like, that's not going to compile. So that's super interesting, right? So here you can see the power of Rust big time. Like there is a macro running and there is a type checking happening in like a string. Yeah. Does that make sense? So like say let's just make this super simple. Say it was just name and I press save. It's like, yeah, but you're also taking an age. You don't take that age up there. They're like, oh, that's very cool. And it's because it's generating code that the compiler is running and saying, yeah, but the code that wants to call this hello function needs to specify an age, but you haven't given me an age. Like, I don't know where to get that from. I can't get it. There is no age in this. So like, what am I gonna do? It's uncompilable, right? And this would be an absolute like runtime bug in most other languages, right? If this was Express, you would happily run it and it would blow up at some point because it couldn't map that thing and it would pass a null there and undefined, and then you would blow up down here somewhere. You would only catch this error at runtime. Yeah, I'm catching it at compile time. Cool, hey?
Yeah, I mean, even if you try to solve for compile time with something like TypeScript, implementing these types of rules in TypeScript is like mind-bogglingly annoyingly complex.
So,
yeah.
Yeah,
absolutely.
Thanks, man.
Yeah.
This has been a very good session. Building a web server in a couple of minutes, very impressive. I think that's a new trick. But yeah, I think the power of is evident. Hey? I think just the protection in the compiler there, limiting the amount of bad code going to production, right? And obviously the benefits of the speed, the memory safety, the concurrency. Yeah, I think that's awesome. And I know it's got like a growing community. And I mean, there's Rustaceans. This is the problem with Rust, right? And I was reading about Rustaceans. People who use Rust contribute to Rust. Not one of these. That's quite concerning. And then there's a Rustonomokion that digs into all the awful details that you need to understand. And then there's a Rustling as well. So talk about a growing, exciting, vibrant community investing in the language to take it forward. So I think it's got a great future, definitely in its infancy, but we're going to see it mature over time and those packages grow. And I'm sure developers will jump on board and especially replace languages like C and C++, where it really makes sense. So thanks for the deep dive today. We went deep in the
Yes, cool. It was possibly a bit deep, but yes, well done for hanging in there.
Yeah, we're going to throw this up onto YouTube or LinkedIn, Facebook, who knows? And share it with the community. From my side, man, thanks for investing in us. It's so good to learn from you, and I love the passion, and it's inspiring. We all want to be better technologists and developers. So, hey team, I hope you've come away from today's session with Tom really inspired to keep going deep in your skills. Yeah. It's like, I remember one question I asked Tom a while ago is like, hey, if you could choose between going wide and going deep, which one would you go? And he said, hey, go both. I'm like, hey, man. So there you go. Go both. Go deep, go wide. And just...
Isn't that exciting?
Yeah.
You've got so much time to do it, right? Your whole life to go deep and wide. Absolutely.
Exactly. But
thanks, guys. That was awesome.
Thanks so much.